Well, good afternoon, everyone. Welcome to Tableau Conference. My name is Richard Wesley, and you are here for a two-part talk between myself and Scott Sherman. And we've both been developers at Tableau for a long time. And so we're going to get two talks today on stuff we are doing that's very forward-looking, both architecturally and computationally. The first part of this will be a talk I gave at a database conference recently on some recent work we've done, incremental computation of common windowed holistic aggregates. And that is a very long title. So the first thing I'm going to be starting off with is explaining just what that title means. And the functions we're talking about fall into two groups. The first one consists of count distinct and mode, both of which have similar implementations. And the other one will be all of the various quantile-related functions, quartiles, medians, and so forth. And then we'll conclude and hand it over to Scott. So let's, as they say, unpack those adjectives. In about 2003, the SQL standard defined a set of new types of functions called analytic functions. We have an example of one here, where we select median of sales. And these functions are computed in windows. And that's what the over syntax there means. And you've got each section of the table is partitioned into independent subsets using the partition by clause. Each partition is then sorted in the same way using the order by clause. And for aggregates, you then have what's called a frame, which is a set of adjacent rows that the aggregate is computed over. And there's two flavors of this. There's row syntax, which means you use an actual physical number of rows. And if you have a single numeric ordering on the column, you can get what's called a range query. You'd say plus or minus 5. Now, the thing about the actual query I wrote here is that I'm not aware of any database that implements it, because median is very difficult to do. And the reason is you need to know about the types of aggregate complexities we have. Aggregates have been traditionally broken into three groups. The simplest ones are called distributive aggregates because you can distribute them. If I asked you to add up 1,000 numbers and you had 9 friends, you could each of them 100 numbers, they could add them up, and then you could take all of the 10 numbers and add them together. So they can be distributed. And a lot of aggregates can actually be done this way. It's not just sum. You can do things like max and min can also be done this way. The next class are called algebraic. And they are just simple algebraic functions of other aggregates that you already have. And the classic examples here are average and variance. But where things get difficult are with what are called holistic aggregates. And they're called holistic because in order to compute them, you have to look at every value at the same time. You can't break them down into smaller pieces. And examples of these include things like count distinct and various quantiles. And these holistic windowed aggregates were not implemented by any RDBMS we could find when we were writing this paper about 9 months ago. And the few partial implementations that we found were inefficient, especially with quantiles. And I'll get to that in a moment. But who cares? Why do you really need windowed aggregates like this? Turns out that, yes, people do want these, especially scientists. And there was a paper at SIGMOD last summer where this was one of the things that the scientists were wanting from the system that these researchers had built in order to do sharing of sort of a sharing of workbooks and queries and so forth system. It was one of the things that they demanded. And many of the kernel smoothers from statistics are these holistic aggregates. And there's this great example here. If you've ever been to Old Faithful in Yellowstone, you know that the geyser has a regular eruption cycle. Well, the thing is that because of the complexity of the caverns underneath, there's 2 metastable states, and it bounces back and forth between them. So if you go and measure the time intervals, you'll find that they do this sort of clustering. They do one, and then they do the other, and it's noisy. And so if you want to do a sort of moving, where am I now, you could do an average or mean, but if you look at that line there, in the middle, it's meaningless, right? It doesn't really reflect what's going on. You could try a median, and that gets you a little closer. But what you actually want for this particular data set is to have a moving mode. And we don't have any database that can actually do that computation. So this being academia, we built on some previous work. Despite the fact that windowed aggregation is over 10 years old, there's only been about 2 important papers that have been done on it. First one was just 4 years ago, and it talked about if you have a whole bunch of these windowed functions, and they all have slightly different partitioning and ordering, how do you collect them together to implement them as efficiently as possible in a query? And they presented 3 different physical operators for doing this, which I won't go into too much. You can read their paper, which is referenced there. But they were full sort, where you just sort the partitioning and the ordering just as one big sort. Hashed sort, where you split it up, you hash the partitioning and sort the ordering, and then another special one called segmented sort, where you can leverage pre-existing behavior. The second paper was presented by the Hyper group about a year ago, and it was about how you go and implement this sort of operator and do efficient computation of the actual functions involved. So they designed a highly scalable window operator based on the hashed sort from the previous work. And they provided some very efficient implementations of distributive and algebraic windowed aggregates. And these are already in Hyper. But what we contributed was we first took the window operator and built it into the data engine. This work was all done before we acquired Hyper. And so it's a very different architecture, and we were able to show that, yes, you can do this, and you can integrate it successfully and get similar performance. We also then provided a bunch of algorithms for implementing some of these more difficult holistic aggregates, and specifically we're going to be doing count distinct, generalized quantiles, and mode. We came up with rules for choosing between the several different algorithms that we provide for each function, and a bunch of measurements showing that, yeah, it got faster. So first, count distinct and mode. These are both done in a fairly similar manner. Now, the naive way of doing count distinct is that you would take a hash set. And every time you get a new value, you throw it in the set. And if it's already there, well, a hash set doesn't add anything new. It says, oh, it's already there. And then you can, when you're done adding all the values from your window, you can just count how many things wound up in the set. And then you clear it and go on to the next frame. And the runtime for this is the number of rows you have to process times the frame size. So it's kind of quadratic, which is another word for slow. So we took on an incremental approach here. And we're going to share this hash table between adjacent frames. So instead of a set, we're actually going to map each value to a count. We don't remove anything. And we're going to count transitions to and from 0 instead of just the size of the hash table. And we're only going to clear the hash table if it's mostly empty. And we'll get to mostly in a little bit. Now, the runtime of this one is just the number of rows in your window, or in your partition, times the change in size between each frame. And if you have what's called a fixed frame, you're saying, well, I'm always going to do plus or minus 3 rows, then the delta as you move to the next frame is 1. And that means that this becomes linear, which is great. Much better in quadratic. And you can see that in our results. For all of these tests, we had a sort of 10 million row table of 2 columns of integers. And we tried various frame sizes, which will usually be along the x-axis there. And we also changed how they varied. So the size is always the same. But for the fixed frames, we just move it 1 each time. For the variable ones, we make it bounce around in a pseudo-random manner, just so we can see how the algorithms stand up to a lot of variability. So the naive algorithm is always quadratic, and that's that one that's curving down the bottom there. The incremental one, once we get around some refresh issues, when you get up to about 100 or 1,000 or 10,000, it becomes linear as we expected. But even when we're varying the frame around a lot, we can still get a significant improvement in performance with the incremental V curve there, which is the variable frame, but using our incremental algorithm. And even when we get up to 10,000, a window size of 10,000, it's over twice as fast as the naive approach. Now, computing the mode, which is the most frequent value, is very similar. You have a hash table, you get the counts, you keep track of what the largest count is, and that's the value that corresponds to that count is the result of the mode calculation. Now, you can do an incremental version of this in the same way. You have the same hash table, but you don't remove things. Instead, you keep track of the current high watermark, or the count for the previous mode. And then when you move to the next frame, you first go and remove the old values, and that might invalidate your high watermark. But then you go and add in the new values, and as soon as you hit that high watermark again, you know you have a new valid mode. Occasionally, you'll be in a situation where you destroy the old mode and can't convince yourself that you've created a new one, in which case you have to fall back to the naive approach and rescan the whole hash table looking for the largest value. And this has very similar performance characteristics to count distinct. And what we get out of this that's different is it seems that losing track of the high watermark, at least for the kind of random data we were using, is very infrequent. And so this approach seems to scale very well and stay linear. Now, the last part is, when do we flush the hash table? Which is the same way of saying, when are empty buckets going to stay empty? And this is related to the notion of autocorrelation. So suppose you're doing a windowed mode of your sales over time. Well, hopefully your sales are increasing over time. So eventually, the smaller sales values will no longer be in use. So how do you detect that? Well, we went and did some experiments here where we checked what's called the value we call tau here. The only thing we have to work with is how many non-zero counts do we have and how big is the hash table. And once we get to 25% of the table being empty, we found that that's the best point to flush it. And this is not the best strategy available, maybe, because there may be other things we can do, but well, the problem is that you can't distinguish when the frame size is smaller than the domain size. So in all of the tests we were doing before, the number of integer values that we could come up with that we were doing the mode of is 100. But if the frame size is only 10, you'll wind up with all of these empty buckets all the time. And so we wind up flushing it more than we might actually need to. But you can't actually tell that that's a situation because you're building a hash table like that for the whole window is kind of the problem you're trying to solve in the first place. So that's count distinct and mode. The other family of functions are the quantiles. First, a brief review of what these mean. A quantile divides a domain, a sorted domain, into equal values. So a quartile would produce 4 equal pieces, and so on. And a median is just a quantile at the 0.5 position. It divides the range into 2 equal pieces. And percentiles are just quantile of the percentage divided by 100. Now, there's a little subtlety here of continuous values versus discrete values. If you have continuous values, then what you may want is a continuous quantile. And if you have an even number of values, there's no middle value. So what people typically do is pick a value between them. So some people average them, some people interpolate them. It doesn't really matter. You just pick one. And so the way we you wind up doing this, though, is you compute two discrete medians on either side and then average them. So the continuous problem reduces to the discrete problem. But doing this sort of thing with in a windowing environment is tricky because you can't sort it. Because you are going to need the data in the original order for when you move the frame. Okay, just because something is the highest value in the previous frame, if it's the last value in the frame, when you move to the next frame, it'll go away. And so we use an old trick of indirection, and we build a set of indexes to point into the previous values in the frame. So how do you compute quantiles? Well, to do that, we first have to review an algorithm called quicksort, which, if you've ever taken a computer science class, you've run into this. And the way this works is very clever. It goes back to the 1960s. You pick a middle value, and then you move in from both ends, partitioning it, and throwing values that are on one side of it on one side, and the other side of the partitioning value to the right. And so you can see you have all the before values on one side, you have all the after values on the other side, and then the stuff you're still processing in the middle. And you actually throw the middle values out to the end just to get them out of the way. And when you're done, you can move the middle values back into position, and then you've got the before and the after stuff to continue sorting. And you can use recursion on that, or you can do, first I'm going to do part A, part B. Now, this algorithm is a classical one, and it has complexity of order n log n. What a lot of people don't seem to realize, especially in the implementations we were looking at in existing databases, is that there's a faster algorithm for doing quantiles. It's called quick select. And in this, you just want to find the kth value. You don't care if the other values are in order. You only want to put the particular value you're interested in position. So you partition around some kind of middle value, just like you do for quicksort. But now these middle values are already in position. So if k is in that range, the index is in that range, you can just pick that value out. You're done. But if not, you can tell which side of the middle your k is on, and then you can just switch to that one side and forget about the other side. And you just keep doing that until you've picked out the value that you want. This is order n, as opposed to n log n. So with these, we can now implement our quantile. For each frame, we'll build an array of indexes into the partition. And then we'll apply quick select to that array and read out the value at index k. We've got a picture here of the data, the original indexes, and then the indexes after we do a quick select, and then the dereferenced values. And you can see we wind up with E, the middle value, in the correct position there. The stuff on either side is not sorted, but it's closer to being sorted. Okay? And because quick select is order of the size of the frame, the complexity of this algorithm is the size of the frame times the number of partitions. So that's wrong. Sorry. Now what we can do when we're in the windowing situation is when we move to the next frame, the idea is we don't disturb the previous index order. We just go through and find the indexes that are now out of range and squish everything down. That will be the old stuff in the picture. And then when we get to the end, we can start putting in the new indexes that just came into the frame. And the data is now still mostly in order, especially if the frame didn't move by much. So by doing this reuse approach, we can get some very measurable improvements. And this algorithm can also be used with variable frames. It doesn't really care how big they are. And that's important because there's actually a better algorithm in the fixed frame case. We call this one replace. If we've only moved one spot, then there's only one index value that needs to change. So we can just overwrite it with the new index. and the data is now still really mostly in order. Not only that, but when we put the new value into the old position, we can check to see if it actually changed the median. If it's on the right side of the median that we're looking for, we don't have to do anything. Okay, so this cuts down the number of cache writes and just becomes very efficient. Another thing that I sort of glossed over in the quicksort is when you're going to pick that middle value, that's actually kind of tricky. And you pick out a couple of values, like one at the beginning, one at the end, one in the middle, but you can get into situations where you get something bad, like you pick values that are actually all at the end because it's unsorted. But by using this algorithm, you can actually make sure that the values you're choosing among to find a middle value are close to being correct. So it also helps the typical quick select algorithm choose a better starting point. Performance of this is still forced to be quadratic, but it's significantly better than the naive algorithm. And we wind up, when we get up to 10,000 elements in our frame, we've got a factor of 12 improvement when you've got fixed frames. And even with highly variable frames, we wind up with a performance gain of about 1.5. So those are the functions. And to conclude, these non-Gaussian statistical summaries are important for scientific analytic work, and they're really hard to compute efficiently. But you can compute them more efficiently by using reusing state between adjacent frames of your partition. And the performance gains from this approach can range from 1.5 to 200 times. And we'll be doing some future work probably to try and improve our coverage and understanding of these algorithms with larger data volumes than 10 million. We're going to look at more skewed data. We were looking at uniform data in these tests. The variable frame sizes that we used were very random, but for range queries, they're a little more fixed. It's just like, oh, we're missing one date, and we said plus or minus 3 days. So somewhere where looking at variable frames that aren't as variable as the extremes that we tested. There's also a possibility of, if the frames vary a lot, there might be some way to rearrange them so there's more overlap between the adjacent values. So you wouldn't go through the partition in order. You'd go through it in a way that maximizes the overlap between adjacent frames. But that's probably NP hard. There's some other holistic functions we've been trying to find, but there aren't a lot of them. And we may have, if we find those, it would be very interesting to try and see if we can apply the same techniques. And because we started off in the data engine, but now we're moving to Hyper, one of the things I'm doing right now is picking these functions up and putting them into Hyper. And if this talk was your sort of thing, the Hyper group will be hosting VLDB next August in Munich. Lots of beer. Alphonse tells me that picture is taken like one day of the year, so don't expect it to look like that. But so that's a plug for the Hyper group. And finally, related sessions for this talk is pretty much anything involving sort of table calcs or statistics. Where this work originally came from is I'm interested originally in pushing table calcs down to the database, but there's also this idea that you want to be able to do this stuff before you do any analytics. So table calcs are related to this, and basic statistics are as well. And with that, I'll turn it over to Scott.
Thank you, Richard. So Richard was talking about how we're trying to speed things up by intelligent algorithms on the database side. I'm going to be talking about getting speed up on the opposite side by pushing more work to the client. So You may have used some of the interesting interactive visualizations. Oh, can I have the slide deck, please? Okay, can I get the computers or somebody back there? Oh. So this is just the browser. Okay. No, I couldn't. Okay, so I guess instead of that. Ah, okay, thank you. Okay, now I'm set. Okay, so start over again. So what this is showing is you want to, what you're used to when you go to a site like the New York Times is they spend a lot of time building these really nice interactive visualizations. So this one is talking about should you buy or rent your house. And they have a lot of different kinds of input you can have in trying to figure this out, because there are a lot of things that go into it. How much does the house cost? What are interest rates? How long are you going to stay there? And so what they built in this set of visualizations is here you can say how much the house is worth. And as you drag it, you can see the visualizations are updating. Even other vizzes, you can see the one at the bottom is updating. It's updating the results here. So you can go explore these things. Well, my house is going to be $225,000 that I'm looking at, and I'm expecting to stay there for 12 years. So I can rent a similar house for less than $757 a month. So what's nice about this interactivity, is that you get a much better sense of your data because you're playing with it and you're seeing things change live. Where's the second monitor? There we go. So the interesting challenge here is that on the one hand, you like that New York Times viz that had a whole team of developers building it, where you have the responsiveness. Things happen immediately as you're dragging, allows you really to explore things. But on the other hand, you want all the power of Tableau. So that was a nice, relatively simple model that you could do entirely in the browser without too much difficulty if you've got a team of developers. But one of the things, Tableau can do a lot more. We've queried lots of different databases. We have lots of complex calculations that we can do. So it's an interesting trade-off between the responsiveness and the power. So here's Tableau Public. Here's a viz that I published that is showing the life expectancy of different countries around the world. The top viz is showing broken down by females. The bottom viz is broken down by male. And some work that we did in Tableau 8 made this a lot more responsive. So as I move my mouse around, you can see tooltips showing immediately based on the country that you're over. You can see the outline of the mark that I'm over. As I drag to select, you can see exactly which marks it's going to select. And this filter here is showing GDP per capita of the different countries. And I want to filter out, say, the low end of the range here. And as I drag it, things are updating immediately. So I created this viz pretty quickly in Tableau. I didn't need a whole bunch of developers on staff, though actually I do have a bunch of developers on staff. But I could author this very quickly, and I got all the nice responsiveness in the browser. So I'm going to talk about both how we did this and how this doesn't actually cover all cases, and some of the challenges of getting more responsiveness in more cases and what we're doing about that. So the kinds of things you think about when you are thinking of responsiveness, there's what we call responsive marks. That's when we moused over and you saw the outline. There's selection and highlighting happen immediately. There's, if you author actions, where when you select or hover over things, it will filter or highlight related information in other visits. You're expecting that to happen immediately as well. And you also expect filtering to be interactive. That's the interesting case. But the flip side is, well, what sorts of things can Tableau do? It can query any of dozens of databases. I've long since lost track of how many different databases we can connect to now. We do lots of complex calculations within Tableau, calculated fields and tabled calcs and forecasting models, reference lines, trend lines, a lot of variety of layout. We can run custom R scripts and now custom Python scripts. We can work with arbitrarily large data sets, millions of marks, and we can do all that fairly quickly. But this is a lot more than a New York Times authored viz is going to do. This, once you see something in the New York Times, that's been boiled down to a much simpler model, much simpler data, and it doesn't do all this complexity. So how do we get both of those? So what we do is we actually have a hybrid model, where if the viz is simple enough for some definition of simple, then we can push enough information into the browser for it to be interactive. The browser client then has enough information that it can give you that feedback immediately. But if it's more complex, we create bitmaps. We send those bitmaps up to the browser instead. So now you have the full power of server, because we're doing all the work on server, but you lose the interactivity because it's just bitmaps up to the browser client. So dig into a little bit more of what that means and how we've been changing things. This is kind of simplified version of what we call our visual pipeline or interpreter pipeline of how we compute vizzes. We start out by querying the database. We apply filters. Now, filters are something that sometimes the database needs to do, or it's better if the database does it. Sometimes there are cases where we need to do the filtering because it's a calculated field. The database doesn't know about it because Richard hasn't pushed that work to the database yet. So we have to do that filtering ourselves. And calculations and forecasting and partition for small multiples, different kinds of layout, highlighting, rendering. And so at the very end of that comes out a bitmap, and we can send that bitmap to the client. So this was the original design of server when we first shipped it, and it's still what we do when the viz is too complex for the browser client to be able to handle it. The great thing about this is it supports the huge, arbitrarily complex vizzes that you can do in Tableau. But of course, the drawback is that it's not very responsive, because we send bitmaps up to the client. When you do anything in the browser client, click on something, drag something, just hover the mouse, those mouse events need to go back to the server. The server does the work, ships up a new bitmap. So what we did in Tableau 8.0, how many people have used Tableau long enough that they use Tableau 8? OK, a lot of you. So we made a big improvement in Tableau 8 where we could get the responsive viz that I just showed you in the browser a little bit ago. What we did was we were working on pushing that line between the server and client back, so that before we do the rendering and selection and highlighting and tooltips and all that, we create what we call a presentation model, which is basically enough information that the browser client can now do that work itself locally. It doesn't need the server involved anymore to do those last parts of the pipeline there. So now we get a lot more responsiveness. What goes into a presentation model? It's kind of, a lot of it would be kind of what you would expect. So that first chunk for a dashboard, those are the different objects you can put in a dashboard: visuals, worksheets, legends, filters, parameter controls, the different kind of UI, information about the text and pictures and web pages you have embedded in your dashboard. Within each visual, a single viz, it's broken down into all the marks that go up there. Information about the axes and headers and grid lines, all the other stuff that goes along with the viz. Reference lines and trend lines and annotations, titles and captions. But then there's also this batch, this last stuff, is we send additional data to the browser client so that we can do some more interesting things than just display the marks. So if we're going to locally highlight, so you've got several vizes, you pick in one and it highlights related information in the others. The only way it's going to know about that related information is if we've sent enough data to the browser that it can do that work itself and figure out what needs to be highlighted. And that allows us to do tooltips locally, highlighting and selection, and a limited amount of filtering. And again, the filtering is the entertaining part here. So look again at this pipeline. Where does filtering happen in the pipeline? The very beginning, maybe even in the database. So let's say we continued to push that line back like we did in 8.0. So filtering impacts everything. So all that complex work we're doing there, we would need to ship code that supports all of that to the browser. OK, so you've sat and waited for several minutes for all this code to download. The responsiveness doesn't matter anymore. We've kind of used up your patience just downloading the code. So how do we make it so that the browser can filter in more cases than it currently can? So this actually explains some of our limitations in when we can do interactive filtering. If a filter impacts the query, if it impacts a table calc, if it impacts totals, we can't do that in the browser with our current approach. So what we're working on is drawing the line in the opposite direction. Rather than trying to push all the work to the browser client, it's push some of the work to the browser client. And so how many people know the difference between an interpreter and a compiler? So a few people with CS background. So basically what we're doing is we're turning our visual interpreter pipeline into a compiler. So that blue chunk there, figure out what data transformations to run, what that part of the work is doing, that's what will live in the server, and that knows about our rich semantic model. You think of VizQL, which knows where fields are rows and columns and marks cards and all that, are data sources with dimensions and measures and rich semantic roles, style sheets. There's a lot of rich semantic information and a lot of code that goes into figuring out if this is the field and it has this role, then we're going to do this work. Well, that step right there, now we know we need to do this work. That's the bottom part there. We're just going to record the data transformations. We have a bunch of logic that figures out what the data transformation should be based on the viz you're looking at, the data you're looking at. And then we just record, OK, now that we've figured that out, here's the data transformation that we need to run. And that's what we send to the browser client. So we've got a much smaller payload that can basically describe that fully interactive viz. There are still cases, of course, where we won't be able to do the work in the browser because, well, it's a trillion rows, and we're not going to shove a trillion rows and have to the browser and have it do the filtering. So there will still be cases where you won't be able to filter locally in the browser, but there will be a lot more cases where you can. So here's kind of the two buckets of information we might send to the client, kind of depending on what the scenario is, and won't send. So I list indirect queries versus direct queries. So what this means is we've compiled our viz. We've got the list of all the data transformations that need to run. We've sent them up to the browser. And the filter now changes the data. But it doesn't change the data transformations. So we don't need to recompile the viz. We don't need to resend the data transformations. All we need to send, we just need to get the server to go issue the query for us and send the data back. But now there is more filtering that we can do because we can do the calculated fields and the table calcs and layout all in the browser, whereas previously we relied on the server for that all the time. But there will be other cases where R scripts or Python scripts where we're still going to have the server do the work. If there's a huge number of marks, it'll still be faster to have the server do the rendering and send a bitmap than it would be to shove all the data up to the browser and have it do the work. So kind of the quick overview then of where we've been and where we're going to. With the first version of server, it was all about sending bitmaps to the browser, sending mouse events back, and having the server do all the work. In Tableau 8, we pushed that line back a little ways by sending presentation models to the browser. And this was enough information that the browser could do some interactivity locally, get things a lot more responsive. And what we're in the middle of working on is, so what I was describing there of turning it into a compiler, our code name for that is the Tableau runtime. We're in the middle of working on that right now. So I don't know when you'll actually see the difference made by it, but that will be a project that you will see the results of hopefully sometime soon. So I'll just leave up the slide. Oh, yeah, so this was Richard's slide for related talks to what he talked about. And we're doing this talk one more time tomorrow. And remember to fill out your session survey for the talk. And I hope you guys enjoyed it. And we can take any questions you might have on how this all works.